Good morning, good afternoon, or good evening, depending on where you are. My name is Zdenk Prikryl, and today I'd like to talk about the custom RISC-V instructions, how we can create them and verify them. Before we dive into the topic, let me just briefly introduce the company, who we are, what we do. So Codasip is a leading provider of RISC-V processor IPs and the tools by which you can customize these IPs. What it means is that you can take the RISC-V IP as it is and use it as it is, or you can take the IP and modify them using our tools. So then you can have some unique selling point in your product. And I have a couple of slides on this one later on. The company was founded back in 2014 in Brno in the Czech Republic, but the technology itself is much older. It's based on more than 10 years of research at the universities here in the Czech Republic. We are founding members of RISC-V International, and we also introduced the first licensable RISC-V IP back in November 2015. Headquarters as well as R&D centers are located in Europe, so we have centers in Czech Republic, in Germany, in France, and so on. And we have also presence around the world, including China or North America. Now, if we talk about the instruction set extensions or extension in general, let me just briefly introduce how the RISC-V ISI is designed. Well, the ISI is designed in a modular way. What it means is that you have the base integer set of instructions, like something like more than 40 instructions, and we have two variants. Either you work with 16 registers or 32 registers, and then there are a couple of optional standard extensions, the ones that are ratified already or will be ratified in the future, such as the M for multiple and division, or C for compact instructions or floating point operations. So then you can pick and choose the combination that you need for your application. But it may happen that actually you need something more than that. You would like to add some key differentiation point, meaning that you need some couple of instructions that help you with the code size or maybe help you with the power/performance. There are many reasons that we can think of why you can go into the non-standard extensions. One thing that I like to mention here is that it's not about the fragmentation. I mean, the RISC-V ISI is designed in a way that allow you to do these things without breaking compatibility with the standard extensions, which means that you can take application that is compiled for the standard extensions and you can run it on your version of the CPU. So in this case, we are not speaking about a fragmentation at all. So I kind of touched this slide. So there are many reasons why you can go into customizations. You can, the reason could be that you need better performance. You maybe need to lower power. Maybe you need to do some instruction fusion to save the code size a little bit. So yeah, there are a couple of reasons why you can do that, and benefits as well. And we can dive into these topics in a couple of more slides. To give you more precise examples how or what you can do, let me just briefly mention two of use cases that we did with our partners or customers. In this case, we will be focused on the DSP and the cryptography, because these are fields that the general purpose is not really best choice, because the performance is not as good as you want. I have two examples here. I have an example with Verify, which is the cryptography case, and then the microsemi, that's DSP oriented. Let me start with the Verify example here. So they have one of the DSA algorithm, and this algorithm does the Galois field multiplication. And in the standard, if you take the standard extensions, then it takes about 54 cycles to do the multiplication. That's a key point on this algorithm. But then you can come up with a single instruction that does the multiplication in a single cycle. When we implemented this single instruction, we measured the size, and it's about 2% more if you compare to the baseline. But if you look at the performance, it's more than 3x, and at the same time, thanks to the instruction fusion, we were able to reduce the code size by 30%. Then if you compare the ratio between the cost on the area side, and then compare the performance and the code size reduction, the improvement is huge here, and it's definitely worth it to have this single instruction that helps you with the application. Another example I can share with you is the microsemi example, and this is something that is related to the audio processing. So basically, they needed a CPU with some DSP acceleration for the audio processing. There were a couple of other requirements, such as that it has to be low power, small area, and they were looking for a really fast solution. So then we did a couple of iterations in this case, and the iterations are shown in this picture, where we started with the base configuration using a standard extension. And the starting point was roughly the same they have in the previous generation. So the starting point is roughly the same. Then we enabled a couple of more items. So we started with the standard extensions. So we enabled the M extension, and we have two implementations. One that is more friendly for power. The second one is more friendly for performance. And as you can see, with the basic one, with the M with sequential multiplier, speed up is already there. The size increase is there, but it's not significant. And even though if you go with the parallel one, you have a speed up already 13x, and the area is not that high anymore. Not that high anyhow. What's really important is that we did one more step, because these are the standard extensions, right? What we did is we created a custom extension. We added a couple of DSP extensions, and then we ended up with more than 56x in terms of performance. Yet the area increase is not that significant if you compare that to the speed up. So the area went like 2.4x higher than the baseline. But if you compare that with the performance gain, it's huge. So therefore, they decided to go in this direction, because it's clear that it's a winner. There are some other benefits except the performance, because this allowed them to use older technology, which saves some money to them. So there are other benefits in this custom extension world. It's not just about the performance or about the power. It can be about also the technology nodes that you can use, and therefore about the money. The big question is, okay, how to choose a custom instruction? How do I know that my instruction is actually worth it? In this case, the common approach is that you need to use profiling tools to find the hotspots in the application, and then you can look at the hotspots and you can try to come up with the new instructions that may help you with the acceleration. You can do instruction fusion as well. Once you have it, you need to reprofile it, rerun the test cases to see the impact, compare the two versions, and you basically do the iterations as fast as you can, because the more iterations you do, the faster you are, and then you can find a nice solution. In the case of our approach, we have profiling tools that guides you through this process. So then the tools will tell you, okay, it's worth it to add this fusion of instruction. Yeah, it is, because the profile tells you so. So there's something important in this approach, that you should be able to do these iterations as fast as possible, and there should be some kind of guidance by the tools. Of course, if you are an expert in the domain, then you can be much faster. But even if you are not an expert, the tools may help you with this one. And now, okay, so we identify a couple of instructions, but then we need to somehow implement them, even in this process. And there are two basic approaches how you can do that. Let's start with the, let's say, manual approach, which means that you need to change a compiler, you need to change the simulator, you need to change intrinsics, low-level programming tools, debuggers, and verify a lot of things. There is nothing wrong in this approach. It's okay approach, but it's challenging because you need to have bigger teams, or at least experienced teams that can do these things, and therefore it can be time-consuming and expensive. So what if you can automate one or two or even all bullets from the list on the left side, because then you can be much more productive and you can reduce the time that's needed and therefore resources that you need for that. And this is the direction that we have chosen in a Codasip, to automate as much as possible from the list on the left side. And how we do it? Well, we have a studio, and the studio is basically a set of tools for fast and easy modification of RISC-V CPUs that we have, or in fact, you can design something from scratch. It was introduced back in 2014, and since then it has been proven by major vendors, and the products that were developed, or CPUs that were developed in a studio, have seen silicon many times. The key point here is that this processor is described using a high-level architecture description language that we call CODO, and you put the information about the ISA as well as about the microarchitecture in this description. So you basically describe the whole CPU, not only ISA, but also the microarchitecture, also the implementation of the ISA. If you look at this language, because this is the key point, it's a C-like language that's not tied with any particular architecture or domain. What it means is that you can describe instructions that are simple enough, like bit manipulation instruction, or you can describe the DSP instructions, including the SIMD or vectors, or some loads or stores with pre or post increments, hardware loops, DSP-oriented operations, and you can, go even beyond that, because CODL is really generic language. And an example is shown on the right side, where you can see a definition of a multi-plan accumulate, where you can see the textual form of instruction, the binary form or encoding of instruction, and then more importantly, the semantics, which, as you can see, is a C style or C code that you use for behavior of instructions, which is quite convenient because it's easy to follow and easy to read and create. Now, if you look at what you can do with CODL, it's a bunch of things, and I already touched a couple of them. So you can have instructions with the multi-input and multi-output operands. I was mentioning scalar and vector instruction or SIMD instructions, of course, the floating point operations, DSP operations. You can also define multiple register files or multiple stack architectures. So this is supported by Studio already and by the language as well. On the microarchitecture side, you can define how many stages you have in the pipeline. You can define the memory subsystem that you have, including protocols, bit widths, everything's then there. You can define the hazard handling, either whether you have a forwarding there or whether you need to stall the pipeline for some time. But we are not stopping at the inner microarchitecture, but you can describe also things like MMU for Linux-capable cores, PMA, PMPs, caches. That's part of the CODL as well, and you can really leverage the high automation in the studio thanks to that. Speaking of automation, let me just briefly touch the outputs that you can get out of the studio, and let me split it into two parts. One is a hardware development kit, or HDK for short, and basically it contains the RTL and one of the free languages, so it can be Verilog, VHDL, or System Verilog. What I like to stress here is that the RTL is human readable. We keep IDs whenever possible. We respect the hierarchy that the user has, and so on. On top of that, there are links back to CODL, which means that if you do some RTL simulation or something like that, then you know exactly which line was generated from which line in CODL, which is really important as well. We are huge believers in verification, and therefore we have a robust story about the verification as well. So Studio generates UVM environment, and I have a separate slide on this one, so let me cover it there. Then there are integration test benches, CDA scripts, system SQL simulation models that allow you to create virtual prototypes. That's part of the ADK. In the case of the SDK, there is the C or C++ LLVM-based compiler, libraries such as NewLeaf or C++ libraries, low-level programming tools, different kind of instruction set simulators, either the fast ones and high-performance ones, or the cycle-accurate one that really matches cycles by cycle RTL. Then you have the debuggers, profilers, documentation generator, ISA visualization, and for the verification purposes, there is also random program generator, or the programs that were generated by the random program generator. So this is just the highlights of the outputs that the studio can give you from the single source processor description. So the point is that I would like to mention here is that thanks to the fact that we automate a lot of bullets from the list that we saw in the previous slide, and therefore we reduce the time that's needed for the iterations, and therefore you can do a design space exploration in really short time. You can have several iterations per day to see the impact of your changes if you need those changes. Again, we have a profiling tools that help you and guide you for this process, so you are not alone there, and therefore you can do these iterations even more efficiently because the profile tells you information about the hotspots, guides you through the instruction fusion and these kind of things. To give you some numbers, let me introduce the work that we did in the case of the bit manipulation extension. Although it's not ratified yet, it seems that it's stable enough. So therefore, we have decided to implement that, and we had a new hire actually a couple months ago, and we basically decided that she's the one who will do the model. And it took her 2 weeks to do the functional model. What I mean by that is that by the end of 2 weeks, we had the SDK that's aware of the bit manipulation, including the compiler that's able to use these instructions automatically or via the intrinsics. We had the instruction set simulator, profilers, and this kind of tools. So then we can easily see the benefits of these extensions in some areas like cryptography, for instance. Then for her, it took another 3 weeks to figure out the timing that we were happy with. And by the end of 3 weeks, we had the RTL, we had verification in place, we had the test benches, we had the random program generator up and running and used by the verification environment. So all in all, it took 5 weeks to single new hire to implement the bitmalip from scratch. It shows you the power of a studio, because even a single engineer can do a lot of things. I was mentioning the verification, and then we are huge believers in it. And this is the reason why the studio comes with the verification methodology. It's UVM based, which means that it's a functional based verification. And therefore, you need 3 elements. One is the design under test. The second one is the reference model. And then, of course, you need the test cases that are used for comparing of the reference model and the design under test, RTL in our case. Now, a user has an option to either plug his own reference model, or he can use the automation in the studio as well, and therefore we can infer the reference model for him as well automatically. The RTL is generated, of course, and then we have a test cases. So now let's see the test cases. Studio comes with 3 sources, or 3 basic sources. One is that we have embedded test suites or torture suites, if you will, inside of the studio that are based on the GCC, LLVM, some in-house suites, and then of course the third-party suites such as Supertest, for instance. This comes or may come with the studio, and you, as a user, as a designer or verification engineer, you can leverage these embedded suites fully automatically. So you just click on the button, and then these tests are used for verification or testing. Of course, you can write the direct tests, which means that if you have some directed tests, you can plug it there, and the test suite will automatically use it, including the verification part. And the last one is a random program generator that I mentioned a couple of times. So it's a tool that's able to generate random streams of instructions. It can read the instruction set from the processor description. So therefore, it's aware of any instruction that is there. You can constrain this random program generator in many ways. You can constrain which instructions or how often the instructions are used. The same goes with the operands, or like register operands or immediate operands. So you can do really a lot of things thanks to these constraints. So all in all, if you combine these three sources together, then you have really high coverage in the end. And this is, by the way, what we are doing as well, because then you can be sure that everything's fine. Of course, you can plug the compliance test suite in, and you can use this test suite as well, although it's not like verification suite, it's more also the compliance suite. If we look at the verification environment itself in more details, so again, it's UVM based, and there are a couple of features embedded in this environment, such as code coverage, which means that you can really simply see the line coverage, the condition coverage, and these kind of things. Then we also added some functional coverage points in that, which means that you can check the protocols that are used on the memory interfaces. You can also see how the register file is covered, how the instruction set is covered. So this is part of the generated environment automatically. In the case of assertions, it's a similar story. So we have some pre-built assertions like checking that the shared resources are treated properly, X propagation, and these kind of things. That's part of this verification environment as well. And we have test cases, so I already covered this one. So that's part of the UVM environment as well. And then on top of that, Codacy provides some VIPs for the audio debugging, including the RISC-V debug module and some checkers on the protocols that comes with the studio as well. This environment is ready to be enhanced as well by the verification engineers. So it means that if you need to add a couple of more assertions, or if you need to add a couple of more cover points or cross cover points, you can do that. It's open, human readable, ready to be enhanced by a verification engineer. So now let's see how it can be used in real life. So for the demo purposes, what we're going to see is a RISC-V processor, which is a CPU that comes with the studio. And it is implementation of the basic RISC-V architecture. It uses a 5 pipeline stages, and it's heavily inspired by the Peterson and Hennessy book about the RISC-V. So the microarchitecture basically follows this book. It comes with the RV32IM or RV64IM with ZICSR. So the privilege mode is there, the M mode is there, and the on-chip debugger is there. So you can take it as a baseline and then build something on top of that. And this is what we're going to do because we will add one DSP instruction. Let's have the average instruction, which means that we take two source operands, and the result is the average value of these two. So let me switch to the different window, and let's do the demo. Okay, so now we have a Studio up and running, and what we can see is that Studio uses Eclipse-based IDE on top of the generators. So we can see the projects on the left side, the main playing route here is the middle, tasks that we will be able to do with the projects, and then of course console that will tell us what's going on. The demo is based on the RISC-V. So what I'm going to do is I'm going to import the default one. And there is plenty of other examples in the dashboard, but for the time being, let me just import the default one that is prepared for custom extensions already. If we go to the custom extensions, then we have to start with the something that we call instruction accurate model, which is the functional view or the specification, if you will. And as we can see, it's already prepared here. So we need to finish this template, and let's start with the definition of this instruction. In our case, is the average, and actually it's used very well with the predefined element here that describes instruction, because we need the R type, which means that we need to have a free register operands, 2 source operands, 1 destination. In the case of the assembly, we need to have our average instruction here, but the rest is the same. So destination, comma, source 1, source 2. In the case of the binary, we don't need to change really anything, because we can use the predefined opcode for the instruction here, as well as for the master group. So this can be the same, and we can focus more on the semantics, which is preferred for us as well. So we have our 2 operands here, then we can write the results back. So the only thing that needs to be finished really is the implementation of the instruction itself, which is quite straightforward in our case. It's we're gonna do addition of 2 and then we divide it by 2 as well. And this is actually what we have to do right now, because we are adding just one single instruction, and the template that is prepared here basically suits our needs completely. So the next step that we need to do is generate the SDK. It's a simple step. Just double click on SDK target, and then let's wait for a minute. So now we have the whole SDK ready, as you can see here in the tasks. So the next step is that we can write a direct test in this case. And the situation is similar. So the project comes with the direct test prepared for the custom extensions already. So basically all we need to do is just add our code into the test. And in our case, let's keep it simple as well. So let's have some tests. So let's have 2 numbers with some values, let's say 2 and 6. Then we need to have some variables, which can be the A equals A and B equals B. And the last step is to just check that the instruction works correctly. So let's use assert for this one. We have the predefined built-in, and the last step is basically write the condition, which should be very simple. It should be like this. So then we will call our instruction, and let's compare that with the compiled result from a compiler. This built-in is generated automatically thanks to the fact that we have this built-in here, and basically it follows the assembly definition. So now what I'm ready to do is run the test. For this purpose, we are using PyTest. So let me constrain a PyTest a little bit more, because in this case we are interested only in our test, not on the whole test suites that comes with the Studio. And let's constrain that to our test only, which is called test X. If I do it, I can right now run testing, and after a minute, we should be able to see the result. As we can see, all tests passed are related to our group. We can see also a nice view in terms of HTML report, where you can see that the tests are passing correctly. We have some skipped tests, and these tests are related to the UVM, because right now we don't use UVM, so the tests are skipped, but the tests that are using the simulators passed correctly. Next step is that, okay, we have the direct tests, we have our specification, so let's implement that, because we have to have the reference model, which is in our case this implementation, and we would like to have the design under test as well. So let's finish it as well. For this purpose, we're going to use the cycle accurate model, and there is prepared files as well. So what we have to do is basically finish the extension, and it's very similar to the IA model, where we have to just finish the implementation. And in this case, the implementation will be similar but not the same. We're going to use a different style. Let's say that we're going to do the shift for the division by 2. And in fact, this is all I need to do in this case as well, because this is the code that is then translated to the RTL. I'm gonna just limit the bit width here a little bit to have more differences in between the implementation and the reference model, but it's really up to the designer. What I can do next is let's see whether we pass UVM. And for this purpose, there is a testing CA. So all I need to do is just click on that button, and then let's check the result. So as we can see, right now, all tests passed, including the ones that are UVM-based. If I now open the report, we can then check that everything's fine. As we can see, we can also check the coverage if we need to. So everything is nice and clean. The last thing I'd like to show you is the RTL itself. So as we can see, it's generated under the HDK directory. We use a Verilog, and if I open the extension file, it's quite straightforward. And as you can, there are links back to Codel. It's kind of straightforward. We keep IDs, so we have our answer variable here. So quite straightforward, quite easy to follow. And with regards to the UVM, as you can see, the full-blown UVM environment, including the reference or Gordon model, if you will, was generated automatically for you. So as you see, the RISC-V CPU is prepared for extensions. It guides you through the process, and it's really easy to do the first exploration of custom instructions, including verification. Which leads to the last slide that I have for today. So let me just repeat some key points to remember. So custom instructions are there. RISC-V specification allows you to do so and actually encourage people to innovate things. It's not a fragmentation because the standard extensions, the ratified one, are there, and you are compliant with these extensions nonetheless, even though you have more instructions in the end. We believe in automation, and we would like to automate as much as we can from the process of the customization, and therefore we have a tool for that. The tool is called CodaZip Studio, and the input to the studio is a processor description in a C-like language that we call Codel. And then we are able to take this description and generate the SDK, including C/C++ compiler, simulators, debuggers, profilers, as well as the HDK that includes the RTL, verification environment, test benches, and so on. We have a verification environment generated as well. So then you can use it, and you can operate it as a verification engineer. That helps you a lot with the checking that everything's fine. Because it's UVM based, you need to have a stimuli. So Studio helps you with that as well. You can have the ones that are already embedded. You can use random program generator. Of course, you can write your own test as well. And the verification story is something that we are using internally for our IPs as well. So we know that it works properly, and we can be sure that the design flow is fine. So thank you for attention. And if you have any questions, don't hesitate to contact me. Thank you.